In this short appendix, I will give you all the details necessary to derive grad B drift. So the situation is the one of a magnetic field that goes out from the plane and with a gradient in this direction perpendicular to B. It means that the field lines will become more compressed by going this direction. What is the trajectory of a particle moving in this magnetic field? Let's consider a positively charged particle. Because of the V cross B motion, the particle will tend to gyrate. Now, while it gyrates, it will find regions where the magnetic field is stronger here. And with a stronger magnetic field, the Larmor radius will become smaller. So the Larmor radius, curvature radius of the trajectory will become smaller. The particle then will go back into region where the magnetic field is weaker, and therefore the Larmor radius is larger, and then will go back into regions where the Larmor radius is smaller, will turn around and come back, etc. Practice what we will have also in this case. Well, we will have a motion of a particle that is rather complicated, but with the guiding center that moves upwards in the direction that is perpendicular to both grad B and B. Okay, let's try to study this analytically. We will consider the limit of Larmor radius that is much smaller than the typical scale over which the magnetic field varies. Where with 0, for example B0, I will denote the value of the magnetic field or of its gradient at the particle guiding center. What is the advantage of doing that? That if we want to know what is the magnetic field acting on the particle, we can expand around the guiding center. And if we estimate this quantity here, this will be of the order of rho grad B, that is much smaller than B0, and therefore we will be able to neglect all the other terms of higher order. Therefore, what we want to solve is basically the Newton equation with the magnetic field that we can expand as here. Now, if we look at this equation, we notice that this term, because of this ordering, this first term will be much larger than the second one. Therefore, what we do, we decompose the velocity as the sum of a velocity that satisfies the leading order term of this equation plus a perturbation, where V0 is the leading order term, the one that satisfies the first order term here of this equation. And as V prime will take into account of this small correction, we expect that V prime will be much smaller than V0. Therefore, V prime will satisfy the equation, where we can neglect the higher order term, as this term is given by the product of two small quantities, V prime and grad B, R grad B. Now, what we are interested here is in solving this equation is in getting the average V prime, the V prime that actually represent the motion of the steady state motion of the guiding center, the drift. So now, averaging over 1 gyro period, this equation here, we have that the first term will give 0. The second one will lead to, well, it's all proportional to the charge, so we can drop the charge. We will have B prime cross B0 plus the zero average of the second term. And we can actually solve this equation by crossing it with B0 in order to get V prime. Now, as V prime is perpendicular to B0 in this direction, we have that the average of V prime, this double cross product, can be solved as we've done for the case of the cross B drift, and as I was saying, the average of V prime will be equal to 1 over B0 squared, B0 cross R dot grad B0 still crossed with B0. Now, to make things a bit easier, let's fix some axes. We will put a system of coordinates with the x direction pointing downwards, the y direction here, and the z direction pointing in the direction of the B field outwards from this plane. Therefore, if B0 is equal to B0 EZ, as it is in the z direction, and similarly this term here, V cross R dot grad B, is in the z direction, more precisely. So if B is in the direction of z, therefore if B0 is equal to B0 Z, and this term here can be evaluated and will still be in the direction of z. More precisely, it will be given by taking into account that the derivative is only in the y direction, by the derivative of b along the y direction times the difference of the particle position along y with respect to the guiding center, which is located at y0. Well, then, if we try to evaluate this term here, what we will have is that we will have to evaluate V0 cross y minus y0 dB dy. Well, here you can now develop V0 along its y and x component, and therefore this will be equal to the y component of V0. This will result into the x component plus the component due to V0x. Now, if we are careful, we actually know what is V0y and V0x, as these are solution of the equation here, that is the solution of an equation with a uniform static magnetic field. Therefore, we have that the particles do a circular motion. V0 does a circular motion, and V0x will be given by, while V0y will be given by oscillation with the same frequency, just shifted by pi over 2. And the y minus y0 can be also evaluated and will be equal to V0 divided by the omega cyclotron frequency sine of omega ct plus phi, cyclotron frequency time plus phi. Phi here is a phase shift that will be determined by the initial condition of the particle. Now we can plug this expression here of V0x, V0y, and y minus y0 into here, evaluate the gyro average, cross it with B, and what we obtain is V prime. And if you do all the calculation, what you get is that this gyro average V prime will be equal to m, the mass of the particles, divided by 2b0 square, v0 of the particle, divided by the charge, dB dy, ex. This is the result in this specific case, in this geometry. If we look at the most general case, what we have is a drift that is given always by the same coefficient in front, m 2b0 to the power 3, b0 square q b0 cross the gradient of b0. This drift, which is also very important in plasma physics, is the so-called grad B drift.